Okay, in this video I just want to describe what is augmented reality and some of the options we have for achieving this. We've already seen some examples, so in simple terms augmented reality you could say is just projecting some graphics on top of a real image. But there is more to it than that, and a bit more variety in terms of the options we have for displaying. So first things first, there's a paper from 1995 by Milgram where he starts to look at a continuum of options that range from the real environment through to the virtual environment. So typically people list these four things here shown on the screen. So there's the real environment, there's augmented reality, there's augmented virtuality, and the virtual environment. And then there's another buzzword where people say mixed reality. So mixed reality therefore refers to these two in the middle. And the real difference between these two is whether you consider the world that you're looking at as being mostly real with a bit of computer generated augmentation, or mostly virtual with a bit of additional data, shall we say, from a video camera representing the real world. So as we're all working at home, I'm running out of time somewhat for slides. So the main technologies that we can quickly cover can be found in this nice review paper here, linked in the notes, Advanced Medical Displays. So this gives you the kind of overviews of the things that we are looking at. So referring to these notes here, if you put them into different categories, then the first one of the types is an optical see-through but head-mounted. Now in modern terms this is typified, shall we say, by the Microsoft HoloLens. So I won't play the video now, but the point is that you're looking through a clear glass lens, so the real world is the real world that you're seeing, and in front of your eyes is projected virtual imagery. So in this review paper, here's an example of a very early one. This one is being head mounted, but the principle is exactly the same. So at Weiss we have about 3 or 4 of these Microsoft HoloLenses which you'll see us playing with. So that's the real world is optical. Your next option might be, again sticking with an optical real world, is the operating microscope. So again you're seeing the real world and the overlay is projected. So you have an optical system, and what you're doing is you're looking through a semi-transparent mirror. So the virtual graphics can be projected right into the eyepiece and you perceive them as being blended with your view. But another one, so if you go through the research literature, there are other options, but if I'm honest, they haven't really made it into clinical use. So I only tend to see them in the research world. But these are what's called sort of augmented, or sort of windows. So here again you see another example. This is also essentially what's going on inside the operating microscope. You have something that kind of projects the computer image. So if you can see my mouse pointer, if we look at this computer display up here, but the person operating the device is simply looking through this semi-transparent mirror. Again, this way they can see the real world and they can see the computer generated image. Similarly in ultrasound is this one here, where you've got an ultrasound probe here taking an image, projecting it up here, and this chap here can see through the plate of, well, it's a semi-transparent mirror. He can see the real world and also see integrated into that view the ultrasound data. So the difference between some of these might be in terms of how do you work out where to put the image, so the calibration. but also whether or not it works for more than one person, and whether or not the person looking at it has a well-defined optical axis, or basically whether or not you know where they're looking. So in an optical microscope, it's quite well calibrated. You're looking down the eyepiece of of an optical system, whereas one of these systems here, you could move your head around, and you would get depth-dependent parallax issues. So the overlay would actually shift relative to the physical reality. But these are all, to say, generally achieved with mirrors. I have seen them used, or at least in the literature, in dentistry, but not widely used in surgery. There's a lot of talk at the moment about using HoloLens and so on and so forth, but again, all in the research world. Philips is buying into this. If you watch the video closely, there is a lot of money being thrown at Microsoft HoloLens and trying to get it into medical applications. So in real clinical terms, it's probably safest to say these optical systems are really just, as it were, the optical microscope, and maybe in the next few years HoloLens or similar devices will prevail. After that then, there's video see-through. So this might sound a bit counterintuitive. So going back to this example here, it's an old one, it's an old picture. Here, again, if you can see my mouse pointer, this chap's wearing virtual reality goggles, so you can't see through them. In front of your eyes is a screen. Mounted on the side of these is a video camera, and the video camera is projected back on the screen, so you can see the outside world by virtue of the video camera. But also then you can feed in the ultrasound data and display it in the correct position once you've done all your calibration and so forth. So this would be an example of a video see-through device. So it's head mounted, it's from the perspective of the user, which is why it's called a video see-through, but it's not an optical see-through. The next bunch of categories are what they call monitor based. So you might have a fixed video camera looking down on the patient, and you just refer to a monitor somewhere in the operating room. But typically where we see these ones, at least with the work we're doing at Weiss, is in the laparoscopic or endoscopic ones. So essentially you have a tracked camera, and quite conveniently you have a monitor that the surgeon is already looking at, and so it's quite a convenient mechanism to overlay your graphics. So one of the famous groups doing a lot of this for the last 10 years or so, well, maybe longer, is the group at ERCAD, who've pretty much pioneered augmented reality. And again, they draw the options here. They show the options here in this paper by Nicolau et al. Suitable options for laparoscopic surgery. So this is what I'm saying. The one on the left would be considered a normal screen with a normal endoscope. The surgeon continues to look at the normal screen, and you can overlay graphics on there. Or they're saying some kind of head-mounted display, so you could just look down at the patient. I mean, in one sense, that might be more convenient if the virtual registration works. The advantage of the one on the left is that at least if the graphics fail you or the registration fails, you just carry on as normal. But they also show this projection-based system here, where you actually have an overhead projector and you simply project it onto the skin. This is shown more adequately here, where in the operating room the users have mounted essentially a projector from a lecture theatre, and they project onto the patient. Now, in this paper it's manually aligned. Getting this accurate is difficult, but also Nicolau also makes the point that even if you were to get it accurate, the problem with a projector-based method is the projector projects from one point and it projects down vertically. So even when it's correct from one viewpoint, if you're looking at it from a different direction, you would perceive it to be in a different depth and therefore at a different position. So the way around that then is to track your eyepiece but then your eyes have to be calibrated to the tracker, so you would see it correctly, but then another colleague wouldn't. So again, lots of these have been proposed in the literature, but not yet making clinical use. The last one then is whether or not you can use basically integrate imaging devices themselves. So Nasir Nawab at Munich has done some work in that area. So I've only really found a good schematic here, but basically on a C-arm X-ray machine they mounted a video camera and a couple of mirrors. So if you imagine, if you again looking at my mouse pointer, given an X-ray source here targeting the patient here, they attach to the side of the essentially the X-ray source, the transmitter, a video camera, but then they put in two mirrors. So this is a mirror and this is a semi-transparent sort of beam splitter. And effectively what you can then do is you can take a video frame, but then you know that it's registered with the X-ray. These pictures here show the B is the camera, the video camera image, D is the X-ray, and therefore C is the combined. So if you were using this on a patient as opposed to a calibration object, you would see in this augmented view, for example, you would see the video of the patient showing their skin surface, but also the X-ray of their internal anatomy. So say you were trying to target a bone or something, they would be intrinsically registered and the two devices are attached together. So as a summary then, augmented reality generally refers to where it's mostly real, but real can be either really real, as in it's with your own optics, your own eyeballs, or the real could be represented by a video image. And then we add some computer graphics. So we've seen in these examples that there are in fact several options for how you might do this: head-mounted displays, Microscope mounted displays, video see-through devices, monitor-based systems, and just intrinsic imaging devices. All of these would count as augmented reality systems, but again with the kind of caveat that most of them currently are somewhat researchy. There are very few commercial ones on the market.